Hello, today we will talk about some algorithms that we can use to find local optimas for nonlinear functions using gradient descent. So let's quick recap what we have. So if we have a function with several variables and we want to find maximum or minimum of this function under some constraints, we can say that we have a constraint optimization, that our space is limited with some functions or some criteria. We also can have unconstrained optimization. So today we will talk about some optimization methods that work with both unconstrained and constrained optimization. You just need to adapt to them. So we will talk about unconstrained case, and bearing in mind that constraint can be done by just limiting the next step so it doesn't go out of our space, of our feasible solution. So let's take a look at first at simple functions. So we have some function f of x, and we want to go from our current value of this function. So here it is xk. So we want to go from this point and our value of f of xk to a new value where the function becomes less or greater. It depends on what we are looking for. So imagine this is the task when we want to find maximum. So we want to find maximum. Then our step will be very easy. So first, we find a direction from this point, xk, in which our function increases. So usually this is the direction, usually is a gradient of this function at point xk. Now, we find the gradient, we find the direction, but when we try to move in that direction, so we try to move to the point xk plus 1, it depends on the number by which we move. So dk is our gradient, but we can multiply this vector by any fixed number, and we need to find what is this number. So one approach, let's say the best approach, would be to find the maximum value of f along this direction. So we calculate f along this direction, and we find what will be the maximum value of this function if gamma, our multiplier, is a variable, but everything else is fixed. So we have a function of one variable. So once we found such gamma, we add it and we move to our new point, xk plus 1. Then we measure the gradient at that point, again find new gamma, and move in that direction again into a new point, and we repeat the process until we find extrema point. So what will be our extrema point? When our dk will be equal to 0 vector, it means that we have extrema point. It can be either minimum or maximum, so we need to check that, but we cannot move after that because our algorithm depends on this dk, and if it is 0, then we don't move, so algorithm stops. So let's take a look what we're doing when we try to find maximum or minimum. So simple algorithm looks like that. At first, we find initial point, which can be found like with random. Then we find the gradient at this point. We move along this gradient direction, and then we repeat the process until we reach maximum or minimum. So if we want to find maximum, then we add gradient. So the gradient is the direction in which the function increases. So if I want to find minimum, I subtract gradient. So I move in the opposite direction. Then moving in the opposite direction makes my function decrease. Sometimes you don't know the partial derivative, so you cannot calculate gradient as it is because you don't have the function itself. You have something that calculates the function, and you don't have analytical form of this function. So if you don't know how to find the derivatives, but you can calculate the function, then you just use numerical approach. So we fix all other variables except for one, and we calculate the partial derivative in this not fixed variable. So we add some small value of epsilon, then we subtract this value of subtracting epsilon. So we calculate function in forward and backward from our point x. And then we divide by 2 epsilon. Why we divide by 2 epsilon? Because the difference between xi plus epsilon and xi minus epsilon will be just 2 epsilon. So we divide by this distance. So because of that being approximation of the derivative, not the exact derivative, it makes this method less attractive because we have some problems. We don't find the exact gradient, but we find something similar to it. Nevertheless, when you don't have any other option, this is the option you go with. So let's take a look at the simple gradient descent algorithm. So we start with some initial point x0. Then we calculate the gradient at point xi. So we are inside the loop. Now we find all the points along this direction. So from point xi in the direction of the gradient. And we select point xi plus 1 with the largest possible value of f if we want to find our maximum value of f. If we want to find minimum value, then we here subtract and want to find the smallest value for minimum. So after that, we switch to another point, xi plus 1, and repeat the process. So what is the termination criteria? So there are some different termination criteria. One of them is to stop, termination stop. So you calculate the number of steps, and you can say that, for example, 1,000 steps are enough. So regardless of how our function behaves, we stop after 1,000 iterations. So we can even improve that. We can remember the best value along this move and return it. Okay. Another stopping point would be to evaluate our gradient and find when the gradient, the absolute value of the gradient, so the length of this vector, of gradient vector, becomes very small. So usually it's some value like 10 to the power of -5 or -10, something like that. Or we can just find the difference between our 2 points and find whatever the length of this vector, and with the same criteria. However, it's similar to gradient because we move in the direction of the gradient. That's the stopping criteria. Next, we can find the best point along the gradient direction using different approaches. So if we want to find maxima, we move in positive direction. For minimum, we move in negative direction again. So if our function is good function that we know the gradient, then we do just simple trick. So we calculate this thing as a function of t and then substitute it inside of f. So we have f function x0. Let's say we want to find maximum plus t times gradient of f x0. So everything here, except for t, is a fixed value because x0 is a point. Gradient f measured at point x0 is also a vector, and t is just a variable. So now we want to find the derivative of that. So we find df by dt and find such value t for which this thing turns into 0. So this is the function of one variable, which is t. So after we found that, we can find the point t. So if we cannot do this, then we look for some algorithms that can search for such t. So what we usually do is like we say, okay, so the smallest value of t is 0. The largest value of t, we usually fix some value. So we don't have like unlimited value of t. So it will be like t max. And then what we do is, okay, let's find the best value t. So 0 is, when we substitute 0 instead of t, it's just the value of f at point x0. So t max we already know is x0 plus t max multiplied by gradient of f. So we know those values. Now we can find where is the best value. So we can, for example, divide it by half, find the value here, and then look. So if this value, for example, is g1, so this value can be lower, greater than those values, and comparing them, we find in which direction we want to go. Then we go here or here, and then divide, etc., until we find. We can use different direct divisions because, for example, here I used dividing by half, but we can have golden section or Fibonacci section search. So if we cannot calculate neither gradient or Hessian in analytical form, so we cannot find those values t very easily, so then we move to another way of doing that. So we do like sequential modernization of our values. So we have our vector x, and now we want to find the best move. So what we do, for example, we have two decays. So we have direction x or y. So what we do is we try to move in all 4 directions. So in positive x, adding epsilon here or subtracting epsilon from x values, or into y direction, and look at all of those 4 values that we get. Imagine we are looking for maximization of the function. So let's say that here I have the value 2, here I have the value of the function 4, 5, and minus 3. So I select the maximum of them, which is 5, and I go in that direction. After that, I try the same approach. So this algorithm will try from 5 again to move in the old point, but we will not select the old point because our current value is the best one. So we can have different values in other directions, so we can move further. So the move is like that, maybe different, and then we reach our point. Well, when does it work okay? If we are not far away from the optimal point. So after some cycles of finding this value, if we don't move from our point to anywhere, what we do is we replace the number epsilon. So here we propose like halving this number, because, for example, let's say we have this function and we start from this point and move to another point because this is epsilon. And then we try to go back and forward, but we skip the optimal solution in between because epsilon is too large. So if we divide epsilon by half, the next step will be going here and finding the optimal solution, and this will end. So how do we stop this method? We just find when we cannot progress, then we halve the epsilon. And if the epsilon becomes too small, then we just stop the process because of the approximation errors. It's just okay to have this answer. So we call it one at a time search because we move to a new point that is different from old point only by one component of x. But sometimes it's too slow of the method. So it can go so far and not reach the optimal value. So sometimes you don't want to do like that. So instead of doing that, we can do that in a better way. We can find the maximum in direction delta in which we tried to move. So in the previous, we said, okay, so this is the initial point. We try to look here, 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 and here. And then after we move, we continue the process again. We repeat the whole process again. So our accelerated search of Rosenbrock proposes us, for example, if the value here was 1, this is 5, 2, 4, and minus 1. So we clearly see that the best way is going down. We just go down until it stops improving. So we go down, only down, until it stops improving. So for example, here I have 5.5, then 5.7, then 5.8, 5.81, and the next point will be 5.79. So it says that we won't go in that direction, we stop. Now we repeat the process with finding a good direction other directions. So when it's just two variables, it's very easy to see, but when we have n variables and n is very large, this way is much better because it works a lot faster. So we improve in one direction as long as it keeps improving. And only once it stops, we change the direction. So the method looks like that. So we try to improve in one direction. Once it stops, we move another direction. Once it stops improving, we move further and so on. So this is way better search because it goes way faster. So the gradient descent, if we want to use it for minimizing, as I told you, we just not add it, but subtract the gradient. So imagine you at this point. So the gradient will look in this direction because, oh, this is the direction of my function to increase. But if you reverse it, take the minus sign, inverse sign. So then we go in the direction of decreasing of the function, and we will go to our local. So let's say that we have not like one value. We have some data set of many points, and our function needs to be minimized on all of them. So let's say we have some function that maps points to some values. And we have a set of points. So this function depends on some parameters theta. So we want it to match what we have. So for example, we have pairs of x1, y1, x2, y2, and so on, xm, ym. So we have those pairs. So x1 is the value from the space x, and y1 is just some value r. So we know that, but we don't know how the real function looks like. We don't know the real function that can map x to y. So we come up with an idea. So let's say that f function, our f theta function of x, will look like some polynomial. For example, it can look anyhow. So let's say that we have some x1 times theta1, x2, some theta2, and etc. So we have this function. And we don't know the theta values that will give us the necessary values of y's. So we measure this function at all given points. And we measure our values of y's. And then we find, oh, they don't match. But we want them to match. So we want to minimize some value. So usually we minimize the error. What does it mean? So we have our function f theta. We measure it at different points xi. We subtract it from yi. So if it matches, the value must be 0. So what function has 0 as the minimum value? Well, for example, square. Our parabola, simple parabola, has minimum of 0 at the point 0. Now we sum it on all our values and we call it loss function. And it depends basically on theta. So it doesn't depend on x, y's, and y, y's because they're fixed values. We cannot change them. They are already fixed. But we can change theta. So now we want to minimize this loss function. So what we do, this loss function is this function j. So we want to find such value for theta that this loss function has its minimum at this theta. And thus we found some approximation of real function that maps x to r with our f theta. So what we do in batch gradient descent, we need to update this whole thing, but m can be large. So that's how it works. But this is the batch. All of them, x1, x2, and etc., xn, are in our batch. So we have some number of epochs. This is the number of iterations, basically. So we find gradient of our loss function on our data xi and our parameters theta. So our loss function is here. Then we update our theta based on old value, our learning rate, and our gradient of loss function. And that's all that we do. So this is the batch gradient descent. However, even though this method is guaranteed to reach some local minimum for just nonlinear function or global minimum for convex function, it is very slow. Why is it slow? Because, as I told you, m can be large. Like, let's say that we come up with an idea to estimate the grades of some students. So we start with the one university, and we have like 400, 500 students. This m is not large. Now we move to country. So we measure all our parameters, all our values for all students in our country, and the value jumps. So it increases a lot. We have millions now, and our function cannot like work like that. I mean, finding the gradient, this can be very hard for some function. So if the data set does not fit into the memory, we cannot operate, we cannot find the gradient and etc., because we need all the data that we use. So also no online learning. What does it mean on online learning? So imagine you came up with this idea, as I said, to measure something, to prognose, estimate something about the students, like their grades or other performance. Now you receive a new data. So if you receive a new data and you want to update the whole function, you need to start process again. So you add the data and you run it to update the theta parameters so they match new data as well. This is called online learning. So if you can do this on fly, so you add new information and it updates the function very fast, then we call it online learning. If you need to go through the whole process and it stops for some time, then it's not online learning, it's offline learning. So we need to store the whole data in our memory, etc. So it's quite bad. Next method is called stochastic gradient descent. Well, it's not so different from the previous one. However, here we don't know the gradient. So the problem here is the gradient. We don't know the gradient, but we want to find that. So what we do, we measure the gradient at only one example in data. So not feeding the whole data set. So as I told you, to find the gradient of the loss on theta, you will need finding the derivatives, partial derivatives of df by d theta on all values xi. So you will need all of them. So stochastic gradient descent says, oh, what if I don't have this whole sum from 1 to m, but I use some estimation. So I say this is not a gradient, but this is evaluation of the gradient, which will be evaluated just on some x. Let's try with some xi. Let's say x1 or any other value. So we remove the sum, so we don't need to feed the whole memory into our algorithm. Whole data cannot fit into the computer memory, or for example, processor memory, cache. So we just feed some example from that data set, and we evaluate our gradient on just that value. So we evaluated this value. Now, we try to update this based on that value. So why is it bad? Well, this x might be bad. We don't know that. It might change the direction of our theta so much that next step will be just recovering from that. We don't know that. So even though this is very fast and allows online learning, because you don't need to remember whole data set, you just receive new data and you insert it into algorithm, stochastic gradient descent, and it just updates the loss function based on the values that you given them. We have the cons of high variance of updates. It means that instead of going in good direction, we can just go in any direction, like in the maze. So we are lost. We don't even know that we are moving in good direction. We can just go in some wrong direction. So that's the drawback of stochastic gradient descent. So batch gradient descent is good because we have some guarantees that we reach local minimum. But here, we are not guaranteed with anything. However, it is fast. So what we do is we combine them. We combine them in mini batch gradient descent. So instead of using the whole data set, we have x1, y1, xm, ym. We divide it into batches, mini batches. So we divide it in one set, S1, another set, S2, etc., ST. So we want T be way smaller than M, but also not as small as 1. So it must be larger than 1. Because if it is equal to 1, it's just the stochastic gradient descent. So now we select some values, and we want to calculate the gradient on those values only. So instead of the previous this one is less variant, so it doesn't go like in the maze. It is more accurate. Still, it is not fast enough, but it is better because it allows you to not fit everything to the memory. Also, to do the online learning, so you get the batch, mini batch. Now you add new data to this mini batch, and that's all. So you just work with that. Usually we do like that. Mini batch size, T size. Mini batch size is M divided by T, which is the size of our mini batch. We don't know that. So what we do, this is batch size, as you see. So what we do here, we try different approaches. So we try learning, finding our parameters for some epochs with different sizes, and we look for the best way. So for example, I plot it, so I have like 10 epochs. So I try one run of 10 epochs when the batch size is like 10. So my learning rate is like that when the batch size is 10. Then I plot, oh, what if I have batch size of 20? So this will be our loss function. Loss function after 10 epochs is less when I run with 20, then I try with 30, 40, etc. So I don't go like for looking for all the values because I know I can fit just M. It will not solve our problem. I have the speed limitation, so I need to stop somewhere based on the speed limitation. So usually we are referring this as stochastic gradient descent sometimes, even though we are using mini batch gradient descent. Well, it's also not gradient descent, not like full gradient. It's still stochastic gradient because we are not based it on the whole dataset. We use just the mini batch. So we can go further. Next, so what are the challenges for those gradient descent algorithms? It's choosing a learning rate. If you remember the t value when we multiplied it by the gradient of function f at point xk. So this value. When we want to find the next is xk plus 1. So how to find this t? So we call this a learning rate. Then we have the annealing schedule because we need to update the values to find the best change of the value. So we want to change learning rate from time to time, and we want to reject new values after some time. So in the beginning, you might jump from one value to another using the gradient descent. As you saw in the previous slide, we didn't check whether the f value at new point was better than f value at the previous. So we could jump, even though we try to minimize, we could jump for increase of the function. Sometimes it's good. Sometimes you don't want to go only in the direction of minimizing because some functions are like bad, like that. So this is the minima we were looking for, but if we only go in the direction of minimizing the function. So we start from here and we end up here, which is way higher than we want. So usually we go in this direction, and when we need to jump this hill to go here, and we don't see that we have the hill. So we allow the jumps of function to increase, but after some iterations, we don't allow the increase of the function to be as large. So we have boundaries for how much we can allow the increase of the function and what is the probability that we allow the increase of the function. And this probability will decrease with the time, but we need schedule. So when this probability will decrease and by what. So that's a whole other method. Then we need to update features to different extent. So we will see that all other algorithms have a lot of different features. And we need to avoid suboptimal minima. For example, if we stuck here, this is suboptimal minima. This is local minima, but it is not global minima in our view. So let's see what are the improvements of this method there are. So all other methods I will show you are also gradient descent methods. The first one is called momentum. So this is very important approach. So it says, okay, let's say that we have been at this point, we started at this point, and then we moved to that point, and based on the gradient, we moved to the new point, and etc. So you see that it jumps left and right instead of going straight because of the gradient. The gradient finds the best approach to increase the function from this point into another direction, but doesn't find the best value overall. So it doesn't see like 100 steps in forward, just from this point into its surrounding area. So what we do is, okay, let's remember the last jump. So the first jump was like that, then the next jump was like that. So when I want to try a new jump that goes up, I know that the last jump was down. So maybe I don't go up a lot, but I go diagonally. And then this will be going diagonally, etc., etc., etc. So how do we do this? We store momentum. So we remember that, okay, let's calculate the gradient. But don't use the gradient as it was. Remember the previous gradient and add it with some value. So this is a fraction. So we call it momentum term. So we set it to 0.9 or 0.8, whichever value you like. So after that, we calculate a new jump and we update our theta on this jump. So the first value, v0, will be just 0 vector. So we just don't change the gradient. But then we calculate v1, which is gamma times v0 plus eta times the gradient of f function. So because of v0 is equal to 0, this will be just eta times the gradient. Okay, so this is like in the simple gradient descent. But what will change in v2? So in v2, we will use gamma v1 plus eta times gradient at function at point x1. So the previous was at point x0. And now it is at point x1. So, well, this gamma is multiplied by v1, which is not 0. This is eta times gradient of f at point x0 plus eta times gradient of f at point x1. Don't forget about gamma that we multiply. And then v3 will be the same thing. So we multiply the previous v2 by gamma, so it will be gamma squared eta gradient at point x0 plus gamma eta gradient f at point x1 plus eta gradient f at point x2 and so on. So that's how it looks like. So what is good with this? Well, gamma is multiplied by itself. So we have this gamma to the power of n, where n changes from 1 to infinity. So we already know what is the value of that. This is just a geometric sequence. So the first value will be in gamma, then 1 minus gamma, which is just some value. So even though this term will affect, but the total sum of all those terms will not be like very large. We know that we can estimate that the whole sum, if we can estimate the gradient, that the gradient at each point, like the length of the gradient does not exceed some value, then we can just multiply by that value, but by eta, and then we will see that this whole thing does not exceed like some constant times constant. So this momentum changes, but not so drastically. It just changes the behavior and allows us to find the optimal solution faster. So let's move further. So then we have Nesterov accelerated gradient. So usually the momentum blindly accelerates down slopes. First computes gradient, then makes the jump. However, now we want to find a better way. So first we make a big jump in the direction, then we calculate the gradient in that jump, and then we update the value. So we want to find a new value that is better. We continue updating the function in the same direction that we had in previous talk. But then we added to the previous correction with a new gradient at a new point. So we already pre-compute what will we get. So let's say that we will get into the new point. Let's say that this gradient is 0. Then Vt will be just the left side, and we will jump into that value. So I want to know what will be the gradient at the new point. So I'm just estimating the gradient at the new point. So I don't do one jump, I do 2 jumps at once. So that's how it looks. It's not exact 2 jumps, but it is estimation of 2 jumps. So the Nesterov update is faster. So you can see that in the picture. So green arrows represent the Nesterov jump. So the brown update, then the red update, then brown update, then the red update. So we had 4 updates, and here I can do this with just 2 updates of Nesterov accelerated gradient descent. So next method will be Adagrad. So this is the adaptive learning rate to the parameters that we can choose. So let's say that in previous methods the learning rate eta was fixed. Now we say, oh no, this is not good for always doing like that. So sometimes you want to change the learning rate in some directions that were not previously seen. So imagine that you already changed one set of the parameters a lot, and other parameters you change like a little bit, only not so frequently. So now you want to say, oh, I'm more interested in changing those parameters that I didn't change a lot. Maybe their change will be a better investment of our time. So what we do is, okay, we have the gradient gt. So this is when we are at the point at time t. So theta t is our parameters. So we are at this point. We evaluated this gradient. Now let's remember all gradients from some point in the past. So let's say we have some parameter which is how much back we look. Let's say some t. Then we can find the sum of all squares gradients I, where I goes from t minus t plus 1 to the t. So how much back we go, and we will call this big G. So what is the square of gradient? It's just you take each component of the gradient and square it. You don't sum up with them, so it's still a vector. So we calculate this G function, which depends on time t, because if as it changes, we also update this. So you can easily update it. So for example, if I want gt plus 1, I don't calculate the whole sum. I just take my gt. Then I need to subtract that term, so t minus t plus 1 squared. And I just add gt plus 1 squared. So that's how it goes. So I can do that easily. It's not calculated the whole sum of t. It's just calculating 1 to 2 sums. Okay. Now, what we do is we update this value, our theta t, but by eta divided by square root of gt plus epsilon. So why do we need epsilon? So for example, we start with some at first step, during the first step, we don't have anything. So the gradient might have 0 values for different components of theta. And we will try here to divide by 0, which is not good. So we add some smoothing term, which is just to avoid the division by 0. Okay, so now what we do, we divide eta by square root of this. So gt is matrix. So how do we do this? It's a vector. So what is the square root? Well, it's simple. So we take our vector g1t, g2t, etc. gnt. We add epsilon to all of them. Then we take square root of each of the components. So we take a square root from the first component. We take the square root of the second component, and so on. So that's how it goes. Now we divide eta by each of them, so we will get vector as well. So we will get vector eta divided by square root of, let's say, gi. So I'm updating component I plus epsilon. I multiply this by gradient t, but not all of that, only component I. And that's how I update the component I of my theta. So it will be our new ith component of theta plus 1. So just how I do, it's like loop over all n values, and for each of them you do this update. So you don't take care that this is a vector or anything like that. So you just do it inside of the loop. And that's how the Adagrad works. So we're adjusting the learning rate based on how much we changed this exact component of theta in the past. So that's the whole idea. Next method is Adadelta. This is also one of the improvements of Adagrad. So here what we do is we, instead of just applying the stochastic gradient descent, we remember the square of gradients before, and we use them like that. So in the previous slide I showed you just the sum. Here this big G of t is different, so new value depends on the previous values and the new value of gradient, and we take the weighted average where gamma is the weight. So we don't forget about the previous values. We remember all the g squared starting from the first, but because gamma gets smaller and smaller after the multiplication, you get gamma in some power. So you eventually don't reflect the change that you had from the first gradient. So now what we want to do is, well, let's estimate our update with the root mean squared error of the gradient, which is just the error that we lacking. So for example, we are at this point and we want a minimum. So we have some error, loss function. This is just an error. So we want the root mean squared of the error of the gradient. So we just calculate that. And now the update of our new delta. So we have at the end our just simple equation of new theta t plus 1, which is theta t plus delta of theta of t, where delta is calculated by this formula 11. So we have RMS of the previous theta divided by RMS of gradients. So how do we get the whole thing? Well, this RMS is just square root of e g squared of t plus epsilon. So we calculate this formula eg, which is easy. Now we need to calculate the formula for theta, which is this formula. So if we want to calculate that formula, we need the previous one, which is just, let's take the initial value. So this value initially will be just 0 or eta, depending on what you want from that. And then you measure the weighted average with the new pre-calculated delta. So you first pre-calculate the delta, you square it, then you change it to this one, then you calculate the square root, and then we divide. So it's way more complicated than the previous methods. So at first we say, okay, usually I would just go with this delta, but now I say, maybe this delta is not so good now. So let's consider the previous jumps I have. And I remember all the previous jumps. And then I update new jump based on the previous jumps. Then I calculate this error and I divide this errors of delta theta by error of the gradient. And then I multiply this by the gradient itself at this point. So it's more complicated than the previous methods. Okay. Now finally, let's go to the last method. Basically, the last method is what most of people use. This is ADAM, Adaptive Moment Estimation. And this method is very popular for more than 8 years now. So it's a very popular method. And it stores running average of past squared gradients, as Adadelta did, and also stores running average of past gradients. Not only squared gradients that Adadelta did, but also momentum. And our update will be based on both of them. So what we do is we store momentum. So first momentum m0 will be 0 vector, and v0 will also be 0 vector. Then when you calculate new gradient for a new value, so you are at the point theta t, you calculate the gradient of our loss function g at theta t, and you store it as gt. Now we calculate new momentum. So okay, let's remember previous momentum with some value beta 1, and we add 1 minus beta 1 times gt, which is already shown here. Then I calculate the average of squared gradients, which we explained at Adadelta, with another parameter beta 2. So they are decay rates, just to forget the first momentums and first averages. So it's just for this purpose. So they must be less than 1. Otherwise, your method will not work. Okay, next, so we calculated mt dt. Then what we do is we bias correct them. So we have our beta 1 and beta 2, and we calculate m hat t using our mt value by dividing it by 1 minus beta 1 to the power of t, because this is the number that we have. Let's remember what we have. So let's say that I multiplied beta 1 from n to t minus 1. So this is how many times I multiplied by that. So what do I have? Let's remember that we will have beta 1, which is the first number, then beta 1, or maybe 1, let's say 1 minus beta 1 to the power of t minus 1, and divided by 1 minus beta 1. This is the sum of geometric progression, the geometric series. So let's open our brackets. We'll have beta 1 minus beta 1 to the power of t divided by 1 minus beta 1. So to get rid of those values, we just use this coefficient. Get rid of the values in the numerator. So it will be bias corrected. Now that's just the whole point. We calculate m hat, we calculate v hat, and then substitute them into the formula. So v hat is also a vector. As you remember, this is the squares of the gradient. So for each component of theta, we will just update the values based on those values. That's all.